अभी तो असली मंजिल पाना बाकी है, अभी तो इरादों का इम्तिहान बाकी है, अभी तो तोली है मुट्ठी भर जमीन, अभी तोलना आसमान बाकी है. Hello everyone, myself Chandrasekhar, welcoming you all to this beautiful session of heat transfer. We will we will have the complete revision of all the formula of heat transfer in this session. Please guys do join me fast, and those who are here, please respond through the comment section if I am clearly audible and visible to all of you. Please respond through the comment section. Mark your presence by writing in the comment box so that we can start our session. Can you guys hear me? Before I start, this is my quick introduction for those who are here for the very first time. Hi Rishi, good evening. Rolex, welcome. Namaskar, Adab, Shubh Sandhya. Good evening. Sat Sri Akal, Assalam Walaikum Wanakam. Once again, I welcome you all from the bottom of my heart to this beautiful session of heat transfer, where we will revise all the formula, all the important formula for the subject through questions. So this is my quick introduction for those who are meeting me for the very first time. And you can connect with me through the mail ID which is there on the top of the screen. And I would strongly recommend you guys to join me on the Telegram as well. That is Mechanical by Chandrasekhar. The link is also shared here at the bottom of this screen. Shall we start? There are a lot of formula. You must have a revision before going for your Barc examination. It is going to be very, very important to improve your score in the Barc 2023 exam. So before we start, let me quickly announce you that on this coming Sunday, there will be a free mega workshop taken by Abhinav sir for all the GATE 2024 aspirants. It is going to be very, very beneficial session. He is going to discuss the important tips and tricks, techniques to clear the GATE 2024 exam. All right. So the timing will be 12:30. You are supposed to register yourself for this workshop that is completely free, and share this information to all your friends as well. So there is the first question on the screen. Please read the question and try to get me the answer. Which of the following would lead to a reduction in the thermal resistance? As you all know, the analysis of heat transfer can also be done using the circuit diagram or the thermal resistance diagram, similar to the electrical resistance. So for conduction, how do we define the thermal resistance? For conduction in plane wall, what is the formula for thermal resistance? Do you remember L by Ka? What is the unit of thermal resistance? What is the unit of thermal resistance for conduction? The unit will be Kelvin per unit watt, right? That is for plane wall. Do you remember the thermal resistance for conduction in case of hollow cylinder? That is given by ln of R2 by R1 upon 2 pi Kl. That is for hollow cylinder. And the thermal resistance for conduction in case of hollow sphere, it is given by R2 minus R1 upon 4 pi K R1 R2. The unit will be Kelvin per unit watt, or we can call it as degrees Celsius per unit watt. Hollow sphere. And in case of convection, thermal resistance for convection is given by 1 upon A into H into surface area, Kelvin per unit watt, because Q convection is written by using the Newton's law of cooling, that is H into surface area available for convection into delta T. If we equate with delta T upon thermal resistance, we can find out the expression for thermal resistance for convection. And the thermal resistance for radiation is having two expressions. One is the surface resistance. When the body is a non-black body, that is given by 1 minus epsilon upon epsilon A. and there is a space resistance between the two surfaces, which is given by 1 upon area into shape factor, isn't it? What is the unit of radiation thermal resistance? Do you guys remember these expressions or not? Please give me yes. Do you guys remember these expressions? So the radiation thermal resistance, the unit is meter to the power minus 2, 1 by meter square. Do you guys remember them? So if you see, in conduction, reduction in thickness of the material. L is the thickness of the material. It is about the plane wall. Reduction in the thickness of material and increase in the thermal conductivity will reduce the thermal resistance. That is correct. Option A is correct, isn't it? Oh, first statement is correct. In convection, stirring of the fluid, when we stir the fluid, H increases, and the cleaning the heating surface, because the heating surface can have the fouling. So cleaning the heating surface will increase the rate of heat transfer by convection. So that is why the thermal resistance will decrease. Convective thermal resistance will decrease because the thermal resistance for convection is inversely proportional to H, isn't it? In radiation, increasing the temperature and reducing the emissivity. If we increase the temperature and reduce the emissivity, if emissivity gets reduced, then the surface resistance will, what will happen to resistance if emissivity gets reduced? Then the resistance will increase. More is the emissivity, more will be the rate of heat transfer due to radiation. So the emissivity gets reduced, that will increase the surface resistance. So statement 3 is incorrect. Only 1 and 2 are correct answers. If emissivity is reduced, it means the rate of heat transfer due to radiation will reduce. So rate of heat transfer due to radiation is inversely proportional to thermal resistance. That is why the thermal resistance for radiation will increase by reducing the emissivity. Do you understand it? So the thermal resistance due to radiation will increase. So only option 1 and 2, only statement 1 and 2 are correct. Option B is the right answer. Do you understand it? The next question. The outer surface of a long cylinder, L is very large, is maintained at a constant temperature. The cylinder does not have any heat source. The temperature in the cylinder will vary. How the temperature in the cylinder will vary? What will be the answer? So for the temperature profile, if we talk about the temperature profile for one-dimensional steady-state conduction, for one-dimensional steady-state conduction without heat generation, there is no heat source, it means there is no heat generation, and having the constant thermal conductivity, then the temperature profile is given by T1 minus T upon T1 minus T2 is equal to X by L. That is linear for plane wall. For the plane wall, the temperature profile will be linear, given by this expression. For a hollow cylinder, it is given by T1 minus T upon T1 minus T2 is equal to ln of R by R1 upon ln of R2 by R1. That is logarithmic for hollow cylinder without any heat source. And T1 minus T upon T1 minus T2 is equal to 1 upon R1 minus 1 upon R divided by 1 upon R1 minus 1 upon R2. That is hyperbolic for hollow sphere. For hollow sphere, it will be hyperbolic. So these are the expressions. So for the cylindrical system, it will vary logarithmic. Can you just let me know if there is a heat generation? If there is a heat generation in the system, what will be the nature of the temperature profile? Can anybody let me know? If there is a heat generation, what is the nature of temperature profile? With heat generation, if Q generation is not zero, uniform heat generation, no Rolex, whenever there is a heat generation, whether it will be in a plane wall, cylindrical or spherical system, the temperature profile will be parabolic. So T is given by Ts plus Q dot X by 2K into L minus X for plane wall. That is for plane wall. And T maximum will be given by Ts plus Q dot L square by 8K. That is for plane wall, parabola. And Q will be linear function of X. Whenever there is a heat generation, the heat transfer rate will become variable. That will be linear function of X. In case of cylinder, in case of cylindrical system, in case of solid cylinder, T is given by Ts plus Q dot by 4K into capital R square minus small r square. So here the temperature will be maximum at R is equal to 0. That is Ts plus Q dot R square by 4K. And for a solid sphere, and the nature of heat transfer rate, Q is a function of R square. That is parabola. Temperature profile will be, heat transfer rate will also be parabola. For a solid sphere, you need to remember these expression. For a solid sphere, temperature profile is given by T is equal to Ts plus Q dot R is Q dot by 6K into capital R square minus small r square. T is the maximum at the center of the sphere. That is given by Ts plus Q dot capital R square by 6K. That is at R is equal to 0. And Q is a function of R cube. It is cubic. How we are getting it as cubic? We can understand this way. Q is given by minus K into 4 pi R square into dt by dr. Because T is a parabolic function of R, dt by dr will be linear function of R, and 1 R square is already there. So R square into dt by dr will become a function of R cube. Similarly, in case of solid cylinder, Q is equal to minus K into 2 pi RL into dt by dr. And because of parabolic temperature profile, the slope is linear. It is directly proportional to R. 1 R is already there, so it will be function of R square. Right? Similarly, in case of plane wall, it will be linear because Q is equal to minus K into A into dt by dx, and dt by dx will be linear function of X. So that will be linear. Right? Let us move to question number 3. Solve question number 3. A composite wall of a furnace. What is composite wall? Which is made up of more materials. More number of materials are involved. It can be composite plane wall. It can be composite cylinder. It can be composite sphere. When a composite wall is having 3 layers of equal thicknesses having thermal conductivities in the ratio 1:2:4, what will be the ratio of temperature drop across the 3 respective layers? So the composite wall can have series combination. The wall can have, what is the answer to this question? They can have series combination of resistances. A composite wall is always analyzed by circuit diagram. Circuit diagram. We draw the thermal resistances. They can be in series or they can be in parallel. So for series resistance, when the heat transfer rate is taking place one after another, or the materials are arranged one after another, then it will be series combination. In case of series combination, the rate of heat transfer remains constant. The rate of heat transfer will remain constant, and overall thermal potential is sum of delta T1 plus delta T2 plus delta T3 and so on. And we can say Q is equal to delta T upon thermal resistance. So from here delta T is equal to Q into equivalent thermal resistance is equal to delta T1 is equal to Q1 into R1 plus delta T2 is Q2 into R2 plus so on, and Q1, Q2, Q are equal. If they are equal, so we will get R equivalent is equal to R1 plus R2 plus R3 plus so on. This is the equivalent resistance, and we can say delta T is constant. Delta T is constant, which can be written as delta T is constant in case of series combination. Delta T, in case of series combination, Q remains constant. Q remains constant in case of series combination, as Q is constant, which is equal to delta T upon thermal resistance. So we can say delta T is directly proportional to thermal resistance, or delta T1 upon delta T2 is equal to R1 by R2. And what is the thermal resistance for conduction in plane wall? L by Ka. So it is inversely proportional to K. So delta T is inversely proportional to K. That will give you the answer. So delta T1 upon delta T2, delta T1, delta T2, delta T3 will be given by 1 upon K1, 1 upon K2, 1 upon K3. So 1 ratio 1 by 2 ratio 1 by 4 will be the answer. Option B. Good evening, Harshit. Welcome. How are you? B is the answer. In case of parallel combination, when do we have parallel combination of resistances? When the heat transfer or the mode of heat transfer are occurring simultaneously. When the heat transfer occurring simultaneously, like conduction is occurring, at the same time convection is also occurring. So this will give the parallel thermal resistance. And in case of parallel thermal resistance, we can say delta T overall thermal potential, which is equal to delta T1 is equal to delta T2 is constant. Thermal potential will remain constant, and Q is equal to Q1 plus Q2 plus Q3 and so on. And Q is equal to delta T upon thermal resistance. So Q can be written as delta T overall upon R equivalent. Q1 is delta T1 upon R1 plus Q2 is delta T2 upon R2 plus so on. Delta T overall is same as delta T1 is equal to same. We will get cancel out. So the expression for R equivalent, or 1 upon R equivalent, will be 1 upon R equivalent will be equal to 1 by R1 plus 1 by R2 plus so on. This is the relation. And because delta T is constant, what is delta T? That is equal to Q into RTH. So Q is inversely proportional to thermal resistance. So we can say Q1 by Q2 is equal to R2 by R1. That is how we can find out the ratio of Q1 by Q2. Is this clear? I hope this is all fine. What about the next question? So we are discussing the related formula through the question. The question is not important. The question might be simple, but all the related formula for that particular question, we are trying to revise them. What is the answer to this question? Again, composite system involving combined modes of heat transfer. Composite system plus combined modes of heat transfer. That is also analyzed using the circuit diagram. There is a parameter defined for composite system involving the combined modes of heat transfer, that is known as overall heat transfer coefficient. What is the unit of overall heat transfer coefficient? What is the unit of overall heat transfer coefficient? U. So Q, which is equal to delta T overall thermal potential upon equivalent thermal resistance, is equal to U into A into R equivalent. That remains constant. Heat transfer rate will remain constant as long as Q generation is equal to 0 and the rate of energy storage is also equal to 0. So from here we can say U into A into R equivalent will be equal to 1, or we can say U is equal to 1 upon A into R equivalent. Right? U is equal to 1 upon A into R equivalent. And what is R equivalent? When there is convection and conduction only, and the materials are placed one after another. For plain wall, composite wall, for a composite wall, area remains constant. So equivalent thermal resistance for inner convection, we will take A is common, 1 upon Hi, that is inner convective thermal resistance, plus L1 by K1 plus L2 by K2 plus so on, and then 1 upon H naught for outer convective thermal resistance. So this is our equivalent for composite wall. This is about the composite wall. So what is the answer? Don't you see option A, Rolex? U is equal to, so A into R equivalent will be this expression. This is A into R equivalent. So 1 upon A into R equivalent is U. So option A will be the answer. It is option A, Harshit. A will be the answer. 1 upon U is equal to 1 upon A into R equivalent. It is 1 upon A into R equivalent. U into A into R equivalent is equal to 1. Do you get it? And for cylinder and sphere, for composite cylinder, for a composite cylinder, there are two overall heat transfer coefficient defined. Q is equal to delta T overall upon R equivalent is equal to Ui into inner area into delta T overall. Did I mention delta T overall? Sorry. Here it should be delta T. U into A into delta T overall is equal to constant. So that is equal to U naught into A naught into delta T overall is equal to constant. So from here we will write Ui into Ai into R equivalent is equal to U naught into A naught into R equivalent is equal to 1. So Ui is equal to 1 upon Ai. What is Ai? 2 pi R1L into R equivalent is equal, and U naught will be equal to 1 upon 2 pi R n plus 1 into L into R equivalent. That is 1 upon Ai into R equivalent. Then it is 1 upon A naught into R equivalent. Clear? So what is R equivalent is given by 1 upon 2 pi L into 1 upon Hi into R1 plus summation of Ln of Rj or Rj plus 1 upon Rj divided by Kj plus 1 upon H naught into Rn plus 1. The limit of J will be from 1 to n. That is R equivalent. For a hollow sphere or for composite sphere, Ai will be equal to 4 pi R1 square and A naught will be equal to 4 pi Rn plus 1 square. So for a composite sphere, if we want to write R equivalent, 1 upon 4 pi will be taken common, 1 upon Hi into R1 square plus summation of Rj plus 1 minus Rj upon Kj Rj plus 1 plus 1 upon H naught into Rn plus 1 square. J is equal to 1 to n. This will be the expression for composite sphere. You can develop on your own, no need to memorize. And Ui into Ai into R equivalent will be equal to U naught into A naught into R equivalent is equal to 1. By using this, you can find out Ui, you can find out U naught as well. Right? So there is another announcement that those who are going to appear for ESE examination, who have cleared the ESE prelims and going to appear for mains examination, then there has already been a course started. You can enroll yourself and you can ask your friends to join our mains, ESE mains practice course for all the branches that has already been started from 3rd of April, and everyone can benefit it. Join this course. It will help you to get the best possible marks in your mains examination. All right. The next one is from the critical insulation. The next question is from the insulation. In current carrying conductor, if the radius of conductor is less than the critical radius, current carrying conductor means a cylinder. In case of cylinder, critical radius of insulation is given by K by H. And critical thickness of insulation is critical radius minus R naught. That is how we can find out the critical. And for sphere, that is for cylinder. And if so, the temperature profile will be like this. This is, let us say, R naught, and this is RCR, critical radius. Up to critical radius, the heat transfer rate will increase. Excuse me. Up to critical radius, the rate of heat transfer will increase, become maximum corresponding to critical radius, and then it will decrease. For a sphere, it is given by 2K by H. And if R naught is less than RCR, if R naught is less than RCR, by increasing radius, as R increases, Q will increase. It will become maximum corresponding to RCR, and then it will start decreasing. But if R naught is greater than RCR, if R naught is greater or equal to RCR, then what will happen? By increasing further radius of insulation, the rate of heat transfer will decrease. Q will start decreasing. So this is what the question is about. So the question says, if the radius of conductor is less than critical radius, so R naught is less than RCR, then addition of electrical insulation is desirable because it will reduce the rate of heat transfer. And once the rate of heat transfer gets increased, then the current carrying capacity of the wire will also increase. It increases the heat loss. R increases, Q will increase. It will increase the heat loss from the conductor and thereby enable the conductor to carry a high current. It reduces the heat loss, that is incorrect. It increases the thermal resistance of the insulation, that is incorrect. It reduces the thermal resistance of insulation. It will not reduce the thermal resistance of insulation. The thermal resistance of insulation will always increase. R conduction will always increase because that is given by L by Ka. By increasing the insulation, the LR radial thickness, by increasing the insulation, the conductive resistance will increase, but the convective resistance will decrease. So the thermal resistance of the insulation will not reduce, it will always increase. So that is the reason D is incorrect. Do you understand option D? Anybody is having any doubt in option D, you can just let me know. Thermal resistance of the insulation is conductive resistance. They are talking about the conductive resistance. By increasing the insulation, the conductive resistance will always increase, but the convective resistance will decrease. And initially, up to some thickness, convective thermal resistance will dominate, and after that the conductive thermal resistance will start dominating. That is why Q will first increase, or we can say R will first decrease, R equivalent will first decrease, and then R equivalent will start increasing by insulation. So that is the reason option D is incorrect. The next question is from the fin theory. What about the next one? Addition of fin to the surface increases the heat transfer if the most important case is infinitely long fin. Infinitely long fin. So Q fin is given by KAM theta S. What is M? M is called as fin constant. Under root of HP by KA. That is called as fin constant or fin coefficient. The unit is meter inverse. It is not a dimensionless parameter. KAM theta S, or we can write it as under root HPKA into theta S. That is the heat loss from the fin. H is the convective heat transfer coefficient, P is the perimeter of the fin, K is the thermal conductivity of the fin material, and A is the cross-sectional area of the fin. Right? And what about Q without fin? If the area is exposed to the outside, if there is no fin, then it is A into H into A into theta S. What is theta S? Theta S is equal to Ts minus T infinity. Ts is the surface temperature, T infinity is the fluid free stream temperature. And Q maximum can be when the entire fin is maintained at the base temperature, Ts. Then heat loss will be maximum, that is H into PL into theta S. So these are the various parameters we need to remember for infinitely long fin. And if we talk about efficiency of the fin, fin efficiency is given by Q actual upon Q maximum. So it will be KAM theta S upon Q maximum is H into PL into theta S. PL is the peripheral area. P into L, perimeter into length is the peripheral area. That will give rise to 1 by ml. Effectiveness of the fin, that is the actual heat loss from the fin to without fin. The heat loss from the fin to that of without fin, that is the ratio. KAM theta S upon H into A into theta S. If you simplify this, then it will be Km by H. So if effectiveness is greater than 1, then we can say Q fin is greater than Q without fin. Effectiveness can be greater than, can be less than 1. Efficiency is always less than 1. Efficiency of the fin is always less than 1. Efficiency of the fin is always less than 1, but effectiveness can be less than 1, can be greater than 1. Effectiveness can be less than 1, can be greater than 1, can be equal to 1. So for effectiveness to be greater than 1, that means Q fin is greater than Q without fin. By adding the fin, heat transfer rate increases. So for that, Km by H should be greater than 1. Or we can put the value of M. So K by H into under root of HP by Ka should be greater than 1. Should be greater than 1. Or we can say this K and this K, we can write it as under root of Kp by Ha should be greater than 1. This is the expression. Or we can say under root of Ha by Kp should be less than 1. Under root of Ha by Kp should be less than 1. Under root of Ha by Kp. Do you understand it? Can we write this as under root of Ha by Kp should be less than 1? What is the correct answer? Isn't it option C? Isn't it option C? Good evening, Free Fire. Welcome. How are you? The correct answer is option C, not B. Question number 6. And the next question is unsteady state conduction or lump system analysis. The most important is lump system. When the conductive thermal resistance is less than 1/10 of convective thermal resistance, or when the Biot number is less than 0.1. Then we can call the system to be lump system, and the analysis is known as lump system analysis. In unsteady state conduction for bodies with negligible temperature gradient, it means temperature is not a function of X. Lump, we can assume the system to be a lump or point mass. The temperature time variation curve is, what is the answer? It is exponential. What you need to remember here is theta upon theta I, that is T minus T infinity upon Ti minus T infinity is equal to e to the power minus Ha upon rho Cv into tau, or e to the power minus tau upon tau star, or e to the power minus Biot number into Fourier number. That is how the temperature varies with time. Tau is time, and V by As, volume per unit surface area, is called as characteristic length. Characteristic length. So the nature is exponential. It is exponential. And what is the Biot number? Biot number is the ratio of conductive thermal resistance of the solid to the convective thermal resistance. It should be less than 0.1 for lump system. What is the expression? We can call it as HLC by K. H into LC by K, where LC is equal to V by AS. Should be less than 0.1 for lump analysis. And what is Fourier number? Fourier number is the ratio of conductive heat transfer rate to the rate of energy storage. Q conduction upon Q stored. That is given by alpha tau by LC square. That is Fourier number. Biot number is used for validity of lump system. Fourier number is used to check the penetration of heat wave across a given depth. Fourier number, Q conduction, where alpha is K by rho C. That is called as thermal diffusivity. Do you remember the formula for thermal diffusivity? What is the unit of thermal diffusivity? Who will tell? What is the unit of thermal diffusivity? K by rho C. That is the property. Tau is the time. Fourier number is not a property, neither Biot number nor Fourier number, but alpha is a property. What is the unit of thermal diffusivity? It is similar to momentum diffusivity. The unit will be meter square per second, isn't it? So that is about the lump system analysis. The next question from the convection. The next one is for convection. What is the answer? For laminar boundary layer, when the Reynolds number is less than 5 into 10 to the power 5, we are talking about external flow. For laminar boundary layer, delta x is given by 5x upon under root of Rex. Delta is directly proportional to root x. And delta x by delta t, the velocity boundary layer thickness upon thermal boundary layer thickness, is related to Prandtl number like this. It is the function of Prandtl number. So we can say if the Prandtl number is less than 1, then delta x will be less than delta t. If the Prandtl number is equal to 1, then delta x is equal to delta t. Delta x is the velocity or hydrodynamic boundary layer thickness delta x, and the thermal boundary layer thickness is delta t. If Prandtl number is greater than 1, then delta x is greater than delta t. So because the Prandtl number is 0.7, and what is the Prandtl number? Prandtl number is given by momentum diffusivity upon alpha, that is mu by rho upon K by rho C. So what is that? Rho getting cancelled out. So mu Cp by Kf is the Prandtl number. Mu Cp by Kf. Kf is the thermal conductivity of the fluid. So the correct answer is option C. And for laminar boundary layer, how the Nusselt number, Reynolds number, and Prandtl number related to each other? For laminar boundary layer, Nusselt number, which is H into L by Kf, is directly proportional to Reynolds number to the power 1 by 2 into Prandtl number to the power 1 by 3. That is, and if we talk about turbulent boundary layer, for turbulent boundary layer, when the Reynolds number is greater than 5 into 10 to the power 5, then delta x is equal to delta t independent of Prandtl number. Delta x, and that is given by 0.376 upon Re to the power 1 by 5. So delta x is equal to delta t is proportional to x to the power 4 by 5. And the Nusselt number is given by Reynolds number to the power 4 by 5 into Prandtl number to the power 1 by 3. That is for turbulent boundary layer. Right? And for internal flow in a pipe, for internal flow, for laminar flow, when the Reynolds number is less than 2000, then Nusselt number, that is H into D by Kf, is equal to constant. The value of constant is equal to 4.36 if the heat flux is constant. The value of constant is 3.66 if the surface temperature is constant. For turbulent boundary layer or turbulent flow, for the turbulent flow in a pipe, when the Reynolds number is greater than 4000, then Nusselt number is proportional to Reynolds number to the power 4 by 5, that is 0.8 into Prandtl number to the power 1 by 3. These will be the expressions for. And for natural convection, For natural or free convection. For natural or free convection, Nusselt number is proportional to Grashof number into Prandtl number to the power 1/4 for laminar boundary layer, and Nusselt number is proportional to Grashof number into the Reynolds number will be replaced by Grashof number, and product of Grashof number and Prandtl number is Rayleigh number. So Nusselt number is proportional to Grashof number into Prandtl number to the power 1/3 for turbulent boundary layer. That is for natural or free convection. Reynolds number is replaced by Grashof number in case of natural convection. All right. The next question from the radiation heat transfer. And the question is from the shape factor. An enclosed body consists of three surfaces 1, 2, and 3. Enclosed body means an enclosure. F11, F12, A1, A3, F33. Then the value of F322 is. So to find F322, we use enclosure theorem. According to enclosure theorem, because it is three surface enclosure, F321 plus F322 plus F323 is always equal to 1. So F322 can be written as 1 minus F321 minus F323. F323 is given as 0.2. This is given as 0.2. So F322 is equal to 1 minus 0.2 minus F321. That is 0.8 minus F321. And F321 can be written as by using the reciprocity theorem. According to reciprocity theorem, A1 F123 is equal to A3 F321. What is F321? That is written as 0.8 minus A1 F123 upon A3, right? A1 is given, A3 is given. So it is 0.8 minus what is A1? 1. A3 is given as 2 into F123. So now our objective is to find out F123 by again using the enclosure theorem, that is F322. Let me call it as equation number 1. So F123 can be calculated. F121 plus F122 plus F123 is also equal to 1. That is enclosure theorem. Enclosure theorem. What is F121? 0.2. 1 to 2 is 0.2. So this is 0.2. This is 0.2. F123 is equal to 1. So F123 is equal to 1 minus 0.4. That is 0.6. Put in equation number 1. Put in equation number 1. If you put in equation number 1, 0.8 F322 is equal to 0.8 minus 1/2 into 0.6. That is 0.8 minus 0.3. 0.5 will be the final answer for this one. Yes, the correct answer is option B. Enclosure theorem, reciprocity theorem, the question will be solved. Is this clear? And the last question for the day, that is for radiation analysis by using the circuit diagram. That is actually from the radiation shield. An infinite radiation shield is inserted between the plates without touching any of them, reduces the heat exchange between the plates. Radiation shields are used to reduce the rate of heat transfer due to radiation. And emissivity of the plate and radiation shields are equal. The ratio of net heat exchange between the plates with and without shield is. So for the non-black bodies, the heat exchange between the non-black bodies Q1 to 2 net, by using the circuit diagram, it is sigma T1 to the power 4 minus T2 to the power 4 upon 1 minus epsilon 1 upon epsilon 1 A1. That is the surface resistance for body 1. 1 upon A1 F122. That is the space resistance. 1 minus epsilon 2 upon epsilon 2 A2. That is the expression. That will be the final expression. I told you surface resistance for body 1, surface resistance, and A1 F122 can also be written as A2 F221 using the reciprocity theorem. For the black bodies, if they are black bodies, if they will be black bodies, then what will happen? Then epsilon 1 is equal to epsilon 2 is equal to 1. So Q122 net in case of black body it will be sigma into T1 to the power 4 minus T2 to the power 4. There are no surface resistances, only the space resistance will be there. This is for black bodies. And for large parallel plates, we can say A1 is equal to A2 is equal to A, and F122 is equal to 1, because large parallel plates can be assumed to be enclosure, two surface enclosure. So if we put these values, then we will get Q122 net will be equal to sigma, if we take A common here, T1 to the power 4 minus T2 to the power 4 upon 1 by epsilon 1 plus 1 by epsilon 2 minus 1. This will be the expression. And if a radiation shield is kept, one radiation shield in between of emissivity epsilon 3, then in that case Q122 net will become sigma into A into T1 to the power 4 minus T2 to the power 4 upon 1 by epsilon 1, 2 by epsilon 3 plus 1 upon epsilon 2 minus 2. This will be the expression. And for N radiation shield having emissivity epsilon 3, then expression will be Q122 net will become sigma into A. It will become sigma into A into T1 to the power 4 minus T2 to the power 4, 1 upon epsilon 1, 2n by epsilon 3 plus 1 upon epsilon 2 minus n plus 1. This will be the expression for N radiation shield. If epsilon 1 is equal to epsilon 2 is equal to epsilon 3, if all the emissivities are same, that is epsilon, then we will get Qn shield will be equal to 1 upon n plus 1 into Q without shield, no shield. So Qn shield divided by Q no shield will be equal to 1 upon n plus 1. This will be the expression if this is the special case. So n is 1 for one shield. So Q one shield divided by Q without any shield is equal to 1 upon n is 1, 1 upon 1 plus 1, 1 upon 2 will be the answer for this one. 1 by 2 will be the answer. Option A will be the correct answer. This is how the questions can be framed from these formula. I hope this is clear. I hope you enjoyed, you were able to revise the concept through these questions. So that is all from my side. You can connect with me through the mail ID, or you can be part of my Telegram group, that is Mechanical by Chandrasekhar. The link is also there here mentioned. So thank you for joining in. Please do not forget to like and share this session so it reaches to everyone else in your friend circle and everyone get benefited. And all the very best for your upcoming Barc examination. Stay safe, stay motivated, and keep doing well in your upcoming exam. Thank you guys. Thank you very much. Take care. Jai Hind.